Hi, thank you very much. My name is James Blair, and as Yasmina mentioned, I am a core infrastructure developer working on the OpenStack project. I work with a team of about 4 core members and several other folks that help us out running the development infrastructure for the OpenStack project. I've been working in this capacity for about 2 years, so I've actually seen the project scale from a very small number of developers to the hundreds of developers that are working on it now. So I'd actually like to start with a poll here to find out a little bit about what your current job function is. So Yasmina, if you could push that, yeah.
All right, and folks, we do have your first poll on the screen. You should see it right there. Please select one of your answers, hit the submit button, and we'll keep the poll up for about 25 seconds. Back to you, Jim.
Thanks. So I'm going to be talking a bit about the infrastructure that we use to manage the project. I'm not going to go into very much detail about what OpenStack itself is. There's all kinds of great resources at www.openstack.org where you can find out about the project, the different components, read about user studies, white papers, that sort of thing. Instead, we're going to be focusing on how we manage to accept hundreds of contributions every day from hundreds of developers all over the world on a very fast-paced, large, and growing project. And it looks like we have a lot of developers attending, test engineers and project managers. I think some of the material in here I hope will be useful to you in your projects as well. So here we have a quick overview of OpenStack, just to sort of put this into context. OpenStack is open source software for building private and public clouds. And sort of the core components are the infrastructure as a service components, computing, networking, block storage, object storage, that sort of thing, identity management. And I guess as OpenStack has matured and grown, we've started to move up the stack a little bit, and we've started adding some more some components, sort of like database as a service and orchestration and things like that. So the project itself continues to grow, and we sort of see it as a framework for managing open source cloud computing projects. This slide lists a number of the projects that we have now. You can see that right there at the top, Nova is sort of the centerpiece of the OpenStack group of components. That's our compute as a service project. But we have a number of projects as well. Those 2 in gray at the bottom, Trove and Ironic, those are new projects that we've just added. They're in incubation, which means that they're new projects. They're sort of establishing their community. They're integrating into our release management process and that sort of thing. And hopefully soon they'll be full-fledged OpenStack projects as well. Almost all of our projects have client libraries as well. So each one of these corresponds to a source code repository. So you can see that we actually have quite a number of different source code repositories involved in the project. In addition to each of the source code projects that I mentioned a moment ago, there are what we call programs or horizontal efforts, which span all of our different projects. we treat those as similarly to projects themselves. They have a project technical lead or a program technical lead, and a group of core contributors and that sort of thing. They span things like documentation, infrastructure, which of course I'll be talking a little bit more about here, quality assurance, release management, upgrade testing. We have a program called Oslo, which is a set of common libraries that we use across all of our projects. It turns out that when you have a lot of different programs which sort of behave similarly but are still distinct, you end up with a lot of common code that you want to share between them. So we actually have a program to sort of reduce the code duplication across all of our different projects and move things into shared libraries that we can use across all of the different OpenStack components to make them behave together, and of course to ease the development and maintenance burden. But all of these programs end up touching infrastructure, which again just sort of makes our job interesting. We build the documentation on every commit to every repository so that it's always up to date. We handle the release management and publishing. So when our release manager decides that everything's finalized, we have quite a bit of automation around making sure that it's published consistently and is available. So all of these programs, they touch infrastructure and they touch all of the projects. And I don't want to give the impression that they're too distinct. There's actually quite a bit of blurring between these. Obviously, you don't want your documentation people just off in a corner working alone. That's not how it works at all. It's documentation and testing is everybody's responsibility, but we have these programs to sort of coordinate the effort across all of the projects in a consistent way. So a little bit about our release management, since it impacts a lot of how we operate. We've adopted a time-based release structure so that OpenStack has a new release ready to go near the end of the development cycle for both Fedora and Ubuntu. So we've sort of timed it so that those two distributions can get OpenStack packaged and in their distributions, so that each new Fedora or Ubuntu release can have the latest version of OpenStack in it. We've designed a lot of our process on the Ubuntu development model, actually. So we have design summits at the beginning of each development cycle. So of course we're a widely distributed group of developers from a lot of different companies all over the world, and we don't work together in an office. So what we do is every 6 months we get together in a location, and we basically spend about a week in these little rooms where we all talk to each other and decide what we're going to do for the next 6 months. So it's a very intensive period, but at the end of that week, we've sort of established the high-level goals for the projects, the new large features we're going to implement, how we're going to get them in, how we're going to test them, and that sort of thing. So getting everybody together getting everybody together in person every 6 months really facilitates how we work the rest of the time, which is largely separate in among a number of companies. A lot of people work from home, that sort of thing. So another major aspect of the way that we do our development is that we develop directly on master, on the master branch. So that's always open. We try to make sure that it's always working and anybody can add new features to it at any time. And then during the release cycle, we have milestone releases to sort of checkpoint our progress so that at the Design Summit, when we've established our goals, we have these milestone releases to make sure that we're meeting those goals in the timetable that we established. This next slide shows a little bit about our contributors. Every release cycle, we look at this, and it changes. It's different all the time. It's really exciting. We have, of course, unaffiliated individuals. It's an open source project. Anybody can just download it and start hacking on it, and we'd love contributions from them. We have quite a few commercial entities that are significantly backing this with staff. So folks like HB, IBM, Rackspace, Red Hat, show up significantly on here. There's nonprofit organizations. There's national and local governments. And one of the challenges that we have to deal with is that the number and the quality and the area of contributions change all the time depending on who's working on the project. I have another poll here. I'd like to find out a little bit about the size of your development projects. How many developers you have working on your development projects. OpenStack, at the latest count, we've had about 800 developers working on our project. And I think Yasmina is going to talk a little bit about this poll that's up.
All right, and folks, poll number 2 is on your screen right now. We'll keep it up for about 25 seconds to give you a moment to respond. And also, if you are just joining us, we'd like to let you know if you open your group chat widget, it's that little widget in your widget tray, open it, type in questions. We're going to have Q&A. So if you have a question for Jim and what he's talking to you about and showing you today, type it in, send it in, and we'll take as many as we have time for. All right, we're going to close the poll now and push the results. All right, it looks like 58.8% have the 1 to 5 developers, 25% 6 to 20 developers. We've got 13.6% of you have 20 to 100 developers, and just under 5% 100 developers. Back to you, Jim.
Thanks. So OpenStack as a whole has had about 800 developers contribute to it across the last development cycle. That's the interesting thing about a lot of our methodology is it scales up and scales down. So of course, if you take all of the projects that we're working on as a whole, we have 800 developers. Some of the individual source code repositories may only have a handful of people working on them. And a lot of what we do works equally well to help manage a large number of contributions from a large number of people, but it also scales down to groups of 4 or 8 as well. So a lot of what we focus on is making sure that our tooling is consistent. We, by centralizing this and by providing a standard set of tools and processes for all of these projects, we make it easier for new companies to onboard employees, for new contributors to join the project. It means that every new OpenStack project doesn't have to reinvent how they're going to test, how they're going to accept contributions, that sort of thing. So it really, I think it's been a big part of how we've been able to grow the project so quickly over the past couple of years by trying to make it easy for new contributors and, of course, trying to make it consistent. The developer infrastructure that we manage to accomplish this encompasses quite a large number of systems, and I'll talk about a few of these, but not everything. Of course, we have code review, which I will talk about later, quite a bit of test and build automation. We have all the usual things that you'd expect. We have source code repository mirrors, package mirrors, that sort of thing. A big part of something that we're learning is that a big part of our we do so much testing that our tests produce quite a large number of logs. So we're actually doing a lot of current work in using Logstash and related tools to try to collect interesting information from all of these test logs that we generate and make it usable for developers. Of course, we have Wiki. We publish docs using the Python Sphinx tools. We do a lot of our work in IRC. It's kind of my office and the office for a lot of developers. It's where we meet and we talk to each other in real time because, of course, we're a distributed development organization and we don't meet at the water cooler or have meetings in conference rooms. So instead, we chat with each other on IRC to coordinate our work and ask questions in real time. All of our projects have status update meetings in IRC, and then the project itself, its administration, we have a technical committee that also meets in IRC, and all of these things are logged in public, and anybody can join in. And then there's a number of collaboration tools like mailing lists, Etherpads, blogs, and so forth. And finally, we use Launchpad for blueprints and bug tracking. Launchpad's bug tracking is very sophisticated and actually has a lot of features that help with a large project that's composed of a number of smaller projects. So a bit about our developer environment. All of the OpenStack components are written in Python. Basically, how we do Python development is a big focus. Our developers usually use the latest Ubuntu or the latest Fedora or the latest Mac OS X on their workstations. But when we test their changes, we usually do it on CentOS or the latest long-term support Ubuntu or Fedora, because those are sort of the platforms that the project is targeting as a whole. We code to the PEP 8 standards because when you have that many developers working on a project, code style becomes important. We have tools that automatically enforce this so that people don't have to spend time nitpicking on indentation and things like that. I mentioned Oslo earlier. That factors a lot of things out. We use virtual ENVs to run our tests in so that it's easy for developers to pull down all the dependencies and test their changes in an isolated environment. We have a tool called Devstack, which is really interesting. It has its own website at devstack.org, and it's a tool that developers use to download and install all of the OpenStack components in a single virtual machine so that they can do their development. So, obviously, if you recall that list of OpenStack components that I had earlier, it's quite a large number, and you wouldn't want to set them all up and configure them by hand. So Devstack does that for you and gets you a fully populated development environment ready to go. If you're technically inclined, it's actually a great way to learn a little bit about OpenStack as well, because obviously you don't have to use it just for development. It'll set up a full OpenStack environment for you with a web dashboard and everything, and you can just start trying it out in a single virtual machine. So I'd encourage you to look at that if you're interested in some of the technical features of OpenStack. And a big part of what we do is we run tests every time that a developer submits a change, because again, our environment is quite complex, and we want to. It takes quite a while to run all of the tests on OpenStack, and so our centralized system does that for developers. So whenever somebody proposes a new change to OpenStack, we immediately start running tests on it, and we try to provide that feedback as quickly as possible, not only to the developers, but the people who are reviewing their code. And finally, a major part of our system is the what we call the project gating, which is how we ensure code quality. It's how we sort of make sure that every developer can always be productive. What it means is that every change before it lands in the main source code repository has to pass its tests. So nobody in the project actually has the ability to merge changes without them passing tests. This is a fully automatic system, so that we know that nothing ever lands unless it passes tests, which means that when you start your work every day, you sit down, you check out the latest version of the repository, and you know that even if overnight lots of changes have merged from other developers, that the test suite passes, and you should be able to start your development without having to figure out what broke overnight and fix somebody else's a problem somebody else introduced. So it's a very egalitarian system. Like I said, everybody is subject to it. There's nobody that can say, well, this probably works, and this passed the test that I think it should that should test it. This applies to everybody, and it's been a big part of how we've been able to accept so many contributions so quickly, doing all of this automated testing, and particularly the trunk gating. Like I said, automation is a big part of the story. This is a little screenshot of our trunk gating system called Zool, which I'll talk a little bit about later. But over in the left-hand column, you can see that every one of those little boxes is a change that it's testing right now for a newly uploaded change. And then the column in the middle, those are changes that are being tested as part of the trunk gating system that are going to be merged once they pass tests. There's a number of other things on this page. All of the automated release processes happen through the system. Pre-releases, post-commit tests, things like that. Basically, this is sort of the center of our project automation, and every action that happens to an OpenStack project goes through this system. So, for instance, whenever somebody tags the repository, this system automatically triggers jobs to build a release based on that tag and publish it to the Python package index and things like that. Here's the process flow for the typical developer. You can see over on the right in the shaded area are things that happen in the developer's local environment. So they might start by cloning a copy of the Nova Git repository. They'll make a new branch to fix a bug. They'll commit their change. They'll use a tool called GetReview, which I'll talk about in a minute, which submits the change to the Garrett code review server. Then Jenkins will automatically start testing that change, triggered by Zool, the tool that I showed you a minute ago. And if reviewers have comments or it fails tests or something like that, then the developer will need to go back and amend their commit and submit it again for review and so forth. Once it's approved by a team of core developers, our convention is that anybody can provide a review of any change, but then for each project there's a core team of developers who are they're elected by themselves. They basically look out for new contributors who are insightful, that know the code base well and provide good reviews, and then they nominate them for inclusion in the core team as well. This team of core developers, once two of them have signed off on a change, then one of them can say that this change is approved and it's ready to go into the repository. So once once a change is approved, then it goes into the automated testing queue, and if it passes the tests, then it merges into master, where then it's available for the next person to come along and update the repository and start their change again. I'd like to have our final poll here, where I'd like to find out what kind of testing that you use in your projects. Pre-merge testing, which is a lot of what I've described now. We in OpenStack we test not only the change as soon as it's proposed for review. We also test it right before it's merged to make sure that it still works. There's sort of the more traditional continuous integration where every time the repository changes, you test to see what's broken. Do you use test-driven development? Do you start all of your development by writing tests and then make sure that typically by writing a failing test, and then make sure that your change fixes that test?
Great, and folks, we'll leave the poll up on your screen for just a few more seconds here, and this is one you can pick as many answers as apply to the question. We do have excellent Q&A coming in already for that portion of the event, so folks, if you are just joining us, want to let you know, if you have a question for Jim and what he's talking to you about and showing you, open your group chat widget, type it in, send it in, and we'll take as many as we have time for. And I'm going to close your poll now. And let's go over the results. All right, Jim, it looks like 26.8% use pre-merge testing, 51% post-merge testing, 29% test-driven development, and 19.5% of our audience today selected all of the above. Back to you, Jim.
Thanks. So in OpenStack, we actually do a bit of everything. Obviously, a big part of what we do is to try to do as much pre-merge testing as possible. There are some things that you just can't do in pre-merge testing, like run a stress test suite for 24 hours. So we try to do a bit of everything as appropriate. Let's see here. So I'm going to talk a bit about our code review system. We use a tool called Garrett, which is developed by Google for the Android open source project originally. It's a standalone patch review system, but it has a number of integration points that we find very helpful. You can run traditional Git style hooks so that every time there's a commit, the system runs a shell script, for instance. You can hit it with JSON queries to get data out of it. It has a streaming event channel, which is actually, we make the most of that. That's how our Zool system operates. And it has extensible review categories, which we found helpful. There's by default, there's the verified, have tests run on this code, and then there's code review as well. But you can add as many other categories as you want, like license compliance, copyright checks, things like that. Here's a screenshot of Garrett. This is sort of the top half of a change view. Over on the left, there's information about the change, the commit messages on the right. Those review categories that I mentioned are underneath. You can see verified, code review, and approved are the categories that we have in our system. And then the people who left feedback leave little votes in those categories. Below that, there's the change set itself. Every time there's a new version of a change, a new patch set shows up here, and so you can see all of the files that are modified and the number of lines that are changed, and that sort of thing. Below that, people or automated systems can leave comments. We actually have a number of both of those here. The first comment is from an actual person. The second is from an automated system. The third is from a different automated system. So we have not only do we run our own tests centrally as part of the project, but we also have a sort of open system where anybody who has a testing environment where they'd like to test OpenStack in their own environment, say they have specialized hardware that isn't generally available, or they have a specific environment that they want to make sure is tested that isn't necessarily the environment that we're testing in centrally in the project. They can contribute testing to the project by subscribing to the Garrett event stream, running their tests, and then reporting back to Garrett. So this is really the view that developers have. This is their primary view in dealing with changes to the project. It's where they review code and where they see reports from the automated testing system. And then a little further down there, the comments keep coming from different people. And finally, at the end, somebody approves the change, and Jenkins runs one last series of tests on it right before it merges it, and those tests pass, so it gets merged into the repository. Here's the diff view. Garrett has a side-by-side diff view, which our developers find very helpful, so it's very easy to see exactly what's being changed. We integrate Garrett with our bug tracking system in Launchpad. So if you mention that a change fixes a bug, it will automatically be updated in Launchpad. So the bug will be assigned to you. We'll link back to Garrett from Launchpad so that people looking at the bug can see the change that's been proposed to fix it, and so forth. This is the sort of list of reviews in Garrett. So you can search for reviews that match certain criteria. You can see the subject of the commit message on the left, the project, the person proposing to change, and so forth. And then on the right are the review categories again. So you can see whether it's passed or failed tests, whether anybody's code reviewed it, and whether anybody's approved it for inclusion in the project yet. So in order to get a change into Garrett, we wrote a tool called GetReview, which just integrates with Git as a subcommand, and it makes it very easy for developers to propose a change for review. They don't have to go through any web forms or anything. They just commit their change, and then they type GetReview, and it automatically pushes their outstanding commit to Garrett for review. So it actually, I've contributed to a lot of projects, and this is, I think, hands down the easiest way to contribute a change to a project that I've ever experienced. This is a general purpose tool. It's not OpenStack specific at all. We maintain it as part of our infrastructure, but we actually have quite a few people using it outside of the OpenStack project. If you're using Garrett, I really recommend looking into GetReview because it'll make your developers' lives a lot easier. So a little bit about the types of tests we run. We, of course, run unit tests, which we run in virtual environments. These are tests that are designed to be easy to run on developers' workstations, but we also run them in our Jenkins setup so that developers don't have to. But then there's integration tests, which are a bit more complicated. They need at least a full virtual machine dedicated to it, if not more. Ideally, we'd run them on real hardware to make sure that all of this stuff works. And that's really where the centralized testing is very helpful to developers. Some of the specific challenges that we've run into while working on this testing infrastructure is, particularly with gating, we need to test the effect of merging a change. So, for instance, if you check out a copy of the repository and you you make a change and you test it, you're testing that change as you wrote it, which is very useful, and it's something that we do. As soon as you upload a change, we'll test it. But these are very fast-paced projects that we're working on, and so we need to make and of course the repositories are going to change while your code is in review. So as soon as somebody approves the change for merging, we need to test whether whether everything is still going to work after that change is merged. So a big part of what Zool does, which I'll talk about later, is to make sure that we're correctly testing the effect of merging changes as opposed to just testing them as they were written. We use cloud computers for our testing infrastructure. We use quite a lot of them, actually. We spin up about 700 complete OpenStack instances every day, and use them to run one test, and then we discard them. So we're actually fairly heavy cloud computing users. Every one of those tests happens on a cloud server running on one of several OpenStack installations. And so we're constantly spinning up new computers, running tests on them, and then discarding those computers and starting the whole process again every day. And of course, we have a large number of similar projects and a lot of different configurations that we'd want to run them in. We have a tool called Garrett Get Prep, which is part of how we make sure that we're testing the result of the change. It makes sure that we test that it checks out the branch, it applies the change as it's going to be as it's going to show up after it's merged, and then we run the tests after that. I'm going to talk a little bit about Devstack Gate, which is the system that we use to run our integration tests. This is the system where we use what we do is we create a new cloud computing instance, and we install Devstack on it, and then we run all of those. We run our integration test suite, and then we destroy it. Devstack Gate sort of solves a number of problems around testing on cloud infrastructure. One of the things that it does is it maintains a pool of nodes that are ready to go at any time, so that we don't have to actually spin up we don't have to incur the cost of spinning up a test node when we're starting a test. And it also creates snapshot images with all of the dependencies that we need on them ahead of time. So basically, this is quite a bit of work going into this to making sure that the tests are ready to go at any given time. And we've sort of smoothed out if the cloud provider is having a slow day or has, a cloud API calls fail or things like that, we've smoothed all of that out, and so that this doesn't affect the actual tests themselves. Another very important tool that we use is Zool, which I've mentioned a couple of times. It's a general-purpose truncating system. It's used not only by we wrote it for the OpenStack project, but a number of other projects are using it as well. The Wikimedia Foundation is actually using it for a lot of their development, which is very similar to what we're doing. Its main focus is doing parallel testing of changes, but where those changes are in a virtual serialized queue. So basically, every time somebody approves a change to to an OpenStack project, we put that change in a virtual queue, and then we start running tests on that change. And as other changes are approved, we enqueue that behind it, and we start running the tests on the change behind it, assuming that the change in front is going to merge. And if all the tests pass, then it means that we can test all of our changes in parallel. And if there's ever a problem, if there's a test failure, for instance, then Zool knows to kick that change out of the queue and then retest changes behind it with the new information that changes ahead haven't merged. Actually have a little an illustration of how that works if you're more visually oriented. You can see here that we've got two projects, Nova and Keystone, and those two little dots represent the head of the source code repository at the time. And so here what we've done is somebody's approved 4 changes. So they've approved Nova change number 1, then number 2, and then Keystone, a change to Keystone, and then a change to Nova after that. And Zool lines them all up in this virtual queue in the order that they're approved. But then it starts testing all of them in parallel. So we'll say that changes 1 and 2 passed their tests, but then changes 3 and 4 did not pass their tests. So Zool knows that since change number 1 passed its tests, it's okay to merge, and so it gets merged into Nova. Same thing for change number 2. It passed its tests as well, and so it gets merged. Change number 3 failed its tests, so Zool kicks it out of the queue and leaves feedback for the developers that, hey, this change didn't pass tests. You need to debug that and try again. But the change behind it also failed, but Zool doesn't know whether that change failed because of something intrinsic to it or just because of the fact that the change ahead of it failed. So in this case, what it does is it starts running tests again, and this time it succeeds, and so it goes ahead and merges that change. So Zool is like I said, it not only runs our truncating system, but it's a big part of our automation in general. We use it to run our post-releases, our post-commit testing. We use it to run our release jobs. It responds to tag events and that sort of thing. And finally, I'm going to talk about one more tool that we wrote. We called Jenkins Job Builder. We have quite a large number of jobs in Jenkins. We have over 500 jobs, and a lot of them are very similar because, again, our projects are very similar to each other. So for every Python project, we're going to want to run the style checks, the unit tests, and then our integration tests and that sort of thing. So we wrote a program called Jenkins Job Builder, which allows us to have templated sets of jobs. So, for instance, you can write just using simple YAML. Here's a job that describes how to run the PEP8 style checker for Nova, and then we can just use that. We can say that there's a Nova project, and it needs to run all of the Python jobs, which is going to include that style job, as well as several other jobs. And so basically with a set of simple YAML files that we keep in our Git repository, we describe these job templates and how they're used and how they're applied to all of our different projects, and that expands into managing more than 500 jobs in Jenkins. So it's I think once we got past having 100 jobs in Jenkins, having a system like this became really helpful because it meant that we didn't have to click around in the web interface anymore to manage jobs. So I think those are all the major things I'm going to talk about. We do have a few questions, so I will take a look at those now. So the first question we have is, do we support Java, or is Python the only language? So the OpenStack project has made the decision that all of its projects are going to be written in Python. That's to help the the code reuse between the projects, to help developers make sure that we have people who can work on the OpenStack computing as well as networking and storage and so forth, and move between the projects fairly seamlessly. Our tools themselves support any language, and in fact, Garrett is written in Java as well as Jenkins and some of the other tools that we use. So within our infrastructure, we actually have a number of projects that are Java and take full use of this infrastructure as well. We manage them in Garrett as well. We do code review on them. We use Jenkins to run their tests and builds, and we're actually doing the same kind of tag-based versioning with these projects as we do with Python projects. So we actually have a lot of infrastructure to manage Java projects as well as Python projects. But the OpenStack project itself, all of the OpenStack components are written in Python. The next question is, can I talk a little bit about the tool used to enforce coding standards? So we started with a tool called PEP8, which checks things like indentation and white space and other important things for Python. We've recently started moving all of the projects to a tool called Flake8, which not only runs the PEP8 style checker, but also runs PyFlakes, which is a really great tool that catches errors like importing objects that you don't use, unused variables, really common mistakes that don't get checked because of the way that Python is run. And it also allows for plugins, and so there are actually a number of OpenStack specific style guides. For instance, how we should write to-do comments in code so that they're easily parsable by other people. What kinds of exceptions we should raise to make sure that our exception raising is consistent and things like that. So these are really project-specific style guidelines. And so we wrote a tool called Hacking, which enforces those style guidelines, and it's a plugin for the Flake8 system. So we're really enjoying Flake8 because it combines not only those two tools, which we find very helpful, but also it allows plugins so that we can do these project-specific checks. Let's see. Another question is, please contrast Devstack and Restack. So Devstack is a tool that was written by and for developers to make developing on OpenStack easy. It's also our de facto implementation for our test suite because it's the thing that developers run, and it's probably the easiest way to get an OpenStack set up and running in our test environment. It's not the only way to test OpenStack, but it's the way that we've chosen to do that in our centralized testing. Restack, on the other hand, is a project. I think it's actually now proposed as an official program. If the technical committee accepts it, then it'll become one. But the idea is that it will provide an implementation test. So it's sort of a reference environment that can be used for things like certifying the use of the OpenStack trademark. That's its end goal. So it's still in its early stages, but the goal is to sort of define how we do that testing, and it's probably going to end up defining a set of things that need to be tested and then how they're going to be tested, which is probably going to end up using the Tempest integration test framework that we already have. There's a question about what databases are supported. There's a number of, some of the projects have different database needs, but by and large, I believe all of the projects support using MySQL or Postgres. We actually run our integration test suite using both of those. There are some projects that can make use of MongoDB as well. And then there may be other answers to that question, but I'm not quite as familiar with them because I don't believe that we're testing any other databases in the upstream integration testing that I mentioned. Right. Let's see. We have a few more questions. How often do we run integration tests? So because we run the integration tests as part of the project gating system, we run them on every commit. We actually run them more than once on every commit. We run them as soon as the commit is uploaded, and then when the commit is in the merge queue, it gets run at least a second time. And not only that, but we actually run several different variants. Like I said, we run MySQL and Postgres. We also test a couple of different message buses, Rabbit and 0MQ. And so some of these different variants get their own tests. And so at the moment, I think we run the integration test suite about 4 times every time that we test a change. And like I said, we test a change at least twice, if not more. So basically the full integration test suite runs on every change at least 8 times, often many, many times more. And so as I was mentioning earlier, dealing with all of that, all of the output from all of that testing is a challenge that we're working on now. Basically, it's a huge resource that we run these tests so many times. And so what we want to do is to try to collect the data from them and not just get pass-fail out of it, but try to observe how things are changing to automatically detect errors, to see if things are slowing down, that sort of thing. And I think, let's see if there are any more questions.
Okay, and we do have a couple questions that have come in. James, do you see a red refresh button?
Oh, yes.
Okay, let's make the refresh load. Folks, we are at Q&A. We will take as many questions as we have time for, so please, if you do have a question for James and all the great information he's been giving you today, please open that group chat widget, type it in, send it in, and he'll answer it while he's with us. Back to you, James.
So There's a question that says, if I understand correctly, it consists of a Cloud OS infrastructure with a development lifecycle integration, so each application team installs whatever they need using the underlying resources. That's close, except that we don't really ask each application team to install this itself. We run one instance of all of this for all of the OpenStack projects. So they all share a single Garrett instance. They all share a single Zool instance and Jenkins and so forth. Of course, we could run more of these. We could run one per project, but in our situation, our projects are so integrated that it actually becomes important that we run a single instance of all of this, so that when we run our integration testing, it understands the relationship with the several different code repositories, so that Nova and Glance and Keystone changes all get tested together. But we do treat it as a shared platform that any of our projects use. And finally, somebody says, comment on the following clarification. OpenStack obviously competes with Amazon AWS and less obviously with VMware. I'm not sure I'm the right person to answer that. There's no shortage of folks in the OpenStack community that can comment on something like that. I'm mostly focused on the developer infrastructure, and we try to be a very welcoming community for anybody who wants to pitch in and join. And as evidenced by that earlier slide, we have a lot of contributors working from a lot of different companies that, in some senses are competitors, but they've chosen to work together on this open source project, which I think is going great. I think we have this huge talent pool from so many different backgrounds, and it's great to see everybody getting together and working on a project like this. And I think that's it for questions.
All right. Oh, it looks like one just came in from Andrew. I'll just read it real quick. He asks, any thoughts, James, on which might be quicker/better for setting up a dev test environment, Devstack or TrySec?
So TrySec is a public implementation of OpenStack. It's designed to basically be a fully functioning cloud provider, except not for use in production. It's so that you can see what the dashboard looks like, try to spin up some compute nodes, but it's not, since it's operated at no cost, it's not really suitable for production use. It can't handle any kind of production load. But it does let you test out the APIs and see the system in action. So if you're a very casual user and you just want to see this sort of thing in action without having to set anything up yourself, TrySec is a great way to go. If that sort of piques your interest and you're interested in maybe doing a little bit more with it, setting it up on a larger system that you control yourself, and there aren't other users on, then Devstack is a great way to go, and you'll learn a little bit about the guts of OpenStack itself at the same time. And then if you're ready to work on a real implementation with actual hardware and multiple nodes and that sort of thing, there are a number of guides put together by our documentation team that'll help you set that up. And there's actually there's a great operations guide that was written by some folks with some real-world implementation experience that will guide you through how to make the right choices for doing a real implementation of OpenStack.
Super, James. And I'm just going to push up the slide that has your contact information on it. Folks, it's right there on the screen. If you do have additional questions or want to follow up with Jim, you can contact him right there. There's his information. Perfect. Okay, people are saying thank you. Great event. Yay. All right, and folks, with that, we are going to say a very big thank you to James for presenting an outstanding webcast for us all today and for sharing his knowledge and expertise. A big thank you to everyone that attended our event today. We hope you benefited from it. And we'd also like to say a thank you to those of you that sent in your questions, because having those questions just adds so much more to our events, and we really appreciate it. As we close out, we would like to say a big thank you to OpenStack today for sponsoring our webcast, and let you all know OpenStack is a cloud operating system that controls large pools of compute, storage, and networking resources throughout a data center, all managed through a dashboard that gives administrators control while empowering their users to provision resources through a web interface. Thank you, OpenStack. Folks, this will conclude today's webcast. Goodbye, everybody.